So I'd like to introduce Girish Joshi from Kilopass right here.
Thanks, Sean. So welcome everyone, and thanks for attending our presentation. My name is Girish Joshi. I'm with Kilopass Technologies, so I manage all the sales in the western region here. So all the way down from Irvine up to the northwest side. So today we'll actually go through what Kilopass does, the space that we address with our memory solutions, and then what portion of the NVM space we address as well with that. So what we'll do is we'll go through the presentation. Please hold your questions till we complete the presentation, and then I'll be here as well to address any questions, any follow-up that you would like. So a little bit about Kilopass. Kilopass was founded back in early 2000 timeframe, and the main market to target at that time was at 180 nanometers, any kind of embedded non-volatile solutions. So traditionally, we always had ROMs. So if you had need for any non-volatile, you had ROMs. You had embedded flash was really not up to the par at that point. But any kind of field programmability or requirements for field programmability really caused the shift into moving from ROMs into solutions what we have at Kilopass, typically using what we call as one-time programmable memories. Okay, so we'll go a little bit into those details. Company standpoint, we are about 50 to 60 employees, growing very, very fast. Over the last 4 to 6 years, we have seen tremendous growth, mainly because the technology is moving into that space. We have applications like IoT, for example, where field programmability is extremely critical. So if you can avoid any mass changes to program your device for a different application, that actually prompted a lot of the need for solutions that we offer. From a patent perspective, we have 80 plus patents. The key in Kilopass technology is that it's extremely scalable. So if you're using different foundries, we scale across foundries, we scale across different process nodes. We work with all the major foundries and IDM foundries as well, and we partner very closely with them. So anytime there's a new process node, being an IP company, we get a privilege of working very closely with them to get started with. We'll go through some of the details later on as well. We do work very closely with security partners, and there's a reason for that. When you look at our NVM solution, the key differentiator in this solution is that you cannot probe what's there inside the memory cell. Any kind of passive or any kind of SEMs will not really expose what the data is inside the memory cells. That is a key differentiator. So in any security applications, our NVM solutions are very widely used. From a customer standpoint, we have upwards of 150, 200 customers already. They keep on using us for different, as they progress through the different geometries, as they're getting down to 20 and 16 as well. We have 400 plus socket wins. And from an overall shipment perspective, we are in so many high volume parts. So we are literally in the tens of billions of units range. So our IP has been pretty much in any device that you use, you'll find at least some chip that uses Kilopass OTP. So what's the overall landscape for non-volatile? So obviously, traditionally, we have always had ROMs. So if you have to have any code that's stored, any bits that need to be stored, ROM has been out there for a very long time. Works very well. That's probably the most compact NVM storage as well. Very small bit cell size. The only limitation being that if you need any changes in the field, that becomes a problem. You have to go through a mass change to actually reprogram the ROM. The second aspect is the second aspect is use of eFuses. eFuses have been out there for a long time as well. They have been used in different applications. Redundancy, for example, always used eFuses or even laser fuses for that matter. The challenge with eFuses, again, bigger area. So if the utilization or if the requirement is small, eFuses work pretty well. The second concern is obviously additional layers. So there are more processing steps, between 0 to 5 steps for programming the eFuse. And the bit cell size is much larger than traditional ROMs. Finally, you do get some design flexibility because that can be programmed in the field as well. But the area limitations will limit you to the sort of the size that you can actually use for the array itself. The most flexible in terms of use model obviously have always been the EPROMs as well as the flash. Extremely flexible. You can actually program that in the factory. You can program that in the customer base as well. The challenge obviously is the number of processing steps and how easy is it to actually have a embedded application with these technologies. So we are seeing use of eFlash coming up as well. Obviously, the endurance is pretty high. So if you have a lot of areas where you need to redevelop code and deploy that to the install base, that obviously is a solution. Then we come to OTP, what we build at Kilopass. Key here is zero additional steps. So what you can do with your standard process, we can actually fabricate that. Literally, there are no additional steps in this. Bit cell size is very small. Fundamentally, it is two transistor devices. One is the select device. Second is the program device. And what we do is we do gate breakdown, and that's what we have worked with very closely with many foundries to establish that, to validate that, and we have been silicon proven for almost 15 years now. From a scalability perspective, literally each and every foundry at almost all the process nodes down to 20, 16, and 14, we have been working at 10 as well. So that effort is always ongoing. We work very closely with our partners. And finally, what you get is design programmability. So the idea is to have one design, and then based on software needs, do the programming in the field based on the application. That is where we are very strong at. That's where all our customers are using us at. So how do we compare regarding area? So if you look in the embedded space, the two other types of memories we see, obviously the laser fuses and the e-fuses. From an area perspective, the most compact is ROM. Very compact. There's absolutely no doubt about it. But anytime you need field programmability, these are the options that you would have. If the use model is between 4 KB to 8 KB, say 16 KB, e-fuses work pretty well. Once the application starts going beyond that, say at 128 KB or so, we see exclusive use of OTP in this space. We have many customers who use us for code storage. Anytime they need to redeploy a new code base, there is a certain flexibility we have, what we call as few times programmability as well. That function is available with our memories, so we can actually employ that as well. From an area perspective, again, you can see if we go up to like 1 MB, the differentiation is very, very, very significant. So with Kilopass OTP solution, it scales with technology at advanced process nodes and overall smaller area in terms of bit cell size. What we are very hopeful about is that at 10, we will have an opportunity of replacing the e-fuses with the OTPs. And really, this will become part of like a foundational IP as well. Typically where all the 60 SRAM cells are. We see that we'll actually get to that point very soon because the need from customers is very high for OTPs. From a foundry perspective, we have been working with so all the way down from 180. We didn't show the older process nodes, but from 65 onwards downstream, we have pretty much support for all the foundries. 6555 seems to be a very, very widely used node for all the IoT applications, and we are actually seeing a resurgence of the 65, typically the LP processes in applications in IoT. So a lot of our focus is actually going into that. So any foundry, even some of the IDMs, we work very closely with them, especially at 65 and 55. Going down to 16, 14, we are seeing applications as well. Again, these are driven by customers, so we work very closely with customers as well as the foundry to make sure that we get all the yields up, make sure all the designs are working very well, and we just get good traction on that front with customers. Where you don't see checkboxes doesn't mean we don't have IP in that space. we constantly work with foundries. Some are in qual, some are in being already built, and maybe certain flavors of that have not been built, but we have coverage pretty much across all the process nodes, across all the foundries here. So what's the application of the Kilopass memories? Um, this sort of articulates it very well. So if you look at what all different chips go into a cell phone, or into any other networking application or wireless application as well, we have been used in almost each and every chip that goes in here. The most common application is code storage. Again, this goes back to security. If you want to, if you have needs of very secure code storage, these are memories which cannot be probed, and that's one of the main reasons that for secure code storage, they've looked at OTP for storing the code. The second application we have seen is calibration, and this is done at test. So if you have any critical analog circuits and you need calibration for those analog circuits, typically during sort of test at the die level, you can actually probe and then calibrate the circuits accordingly, and then store the calibration information on the OTP. This has been a very widely used application. Many customers have actually used this, and in analog side, we specifically find this application very heavily. Couple of other areas that we are used very well is yield and defect data. So this is in the image sensing applications. So typically, you may have some dead pixels, and the way to work around that, manufacturers found that they can actually identify which pixels are bad, store those locations in the OTP, and then the software will actually take care of it. So any interpolation, extrapolation for the image side of things can be done via software. And so that actually helps them on the yield side as well when they use OTP in their design side. A very critical function we serve is in the DRAM space. In DRAMs, obviously, you have redundancy. And there is need for redundancy because, again, if you have any bad data or any memory locations which need to be corrected, we can actually create, we are actually being used in the repair side of things to find the redundant columns and then program the OTP to then use the redundant columns in the memory arrays. So this function has been used by key leading DRAM manufacturers, and we have already gone to production with that solution. And again, these are extremely high volume parts, so that sort of adds the volume component to the IP that we present as well. Finally, any kind of crypto keys, any security on that front, we have several customers doing that. In this case, we have shown one with HDMI security, where we actually store the keys, again, from a security perspective. So one thing we are learning in the IoT space, and we have a lot of customers, a lot of interest coming up very recently. What we are hearing is, obviously, there are a lot of key technologies that people are working on, lower process nodes that they're working on. From their perspective, their differentiation is not in how fast the chip is or how fast the design is. Their differentiation is in the software implementation. And for them, again, the code storage, the software itself is extremely valuable. So where we see playing very heavily is mainly where we store the software and the security aspect around the code storage. That is what we are focused on. That is where we are being used very widely in the IoT space. So what makes us secure? So what's this key about security? So if you look at a ROM, here you are basically programming by burning or making or not making a contact. If you probe that, that's very visible. You can actually see exactly which bit is programmed, which is not. Here we have 2 bit cells. And so what you see here is one of the bit lines, and then you have the access transistor, and then you have the program transistor. Looking at the cross-section, there is no way to tell if a 1 has been programmed or a 0 has been programmed. We do this by creating a resistive path between gate and source. So a resistive path is not, you cannot detect that in silicon. Extremely secure. Any kind of contrast checks will not catch what kind of data you are storing in there. That's what makes Kilopass OTP extremely secure. and the application in security is a result thereof. So passive attacks, semi-invasive attacks, and invasive attacks. No one has been able to break into the code that's stored in the OTP. So that makes us very viable in the security applications. From an overall application perspective, we are seeing use in pretty much all these different areas. In the mobile space, without a doubt, in the wearables. All of these are sort of different variations of IoT. Bluetooth is a very big area that we work in. And in general, wireless, because a lot of the subscriber information has to be stored. That has to be critical. And secondly, that is programmed in the field. So all of these capabilities are satisfied by the OTP, and they're very widely used in that space. Another area we are finding use for it is in the smart home area. So a lot of the controllers that we'll soon start seeing inside our house, the Nest and all these different products, they will have need for OTP, because again, it's programming that they will need to do remotely, sort of in the home environment or in the work environment. So the key benefits of the Kilopass NVM: low power, it's NVM, so it's instant on, very small, dense footprint, field programmable, secure, and obviously low cost if you have to rewrite or re-update some of the code in the field. So thank you all for attending. If you have any questions, I'll be here, so feel free to ask. We would love to come and visit you and work with you to solve any NVM.
Girish,
Thank
question here. Oh, I'm sorry.
Yes, thank you. My name is Pierre. I'd like to ask you a question. So this is a reprogrammable, right, non-volatile memory,
That's
right?
That's right.
And so how do you make it secure? Not to, how do you make it secure, essentially?
Right. So there are two aspects to security. One aspect is just fundamentally being a device that's being manufactured. There's no way to actually probe the value itself in the bit itself. The second aspect of security is our applications are, so we have security partners for whom security is extremely critical, and these are all crypto keys and in that area. We have tamper-proof capabilities in our memory. So if someone's trying to do some kind of a voltage scaling, we have the circuitry around the memories, which will essentially disable it for when we find tampering. So these capabilities we have already built in inside the memories. We actually call this particular memory called as secure code, which is tamper-proof. And then obviously the memory by innate is not possible to probe as well. So we have different levels of security in that space.
Mostly in software.
Pardon? So there'll be a software protection, but this is a hardware protection. So if someone's doing some kind of voltage scaling to detect the value inside, we'll disable the memory. And obviously you won't be able to probe it either. So there are two levels of security here. Thanks.
Hi, I had a quick question. How does the area compare to Sidance, your competitor? Like say for a 512 kilobit block on 55 nanometers. What's the...
So typically, if you look at different memories, right, different OTPs as well. So Sidance is one of them. The way the programming is done is very different. And the needs are different as well from a customer standpoint. From an area perspective, we can actually go back and look at certain specific samples. The key is if there is any kind of layer changes or any kind of processing differences, what we really support is no changes in the processing steps. Right? So that is a true differentiator. Security, another differentiator. So memory area-wise, hard to say exactly how it will compare at this point. But yeah, it's possible that they could be more denser, or certain cases we could be more denser. It really depends on the application.
Question? Okay, I think what we're going to do is, so stay put.